Hello, I am Bruno Fontana da Silva. This is a recorded presentation of the work Design of a Low Complexity Receiver for Uplink SCMA with Multiple Receive Antennas for the 2021 IEEE Statistical Signal Processing Workshop. The co-authors of this paper are Juliana Camilo Inácio, Luiza Scharf, and Professor Bartolomeu Ferreira Uchôa-Filho. These are the contents of the presentation. I will start with the motivation, and then we'll move through the system model, multi-user detection algorithms, results, and conclusion. Non-orthogonal multiple access, NOMA, is a training technique that has been proposed for the next generations of communication systems. Sparse code multiple access, SCMA, is a branch of NOMA based on code domain multiple access and is the scope of this work. Either general NOMA or specifically SCMA enable reliable communication in overloaded scenarios where the number of users is larger than the number of available orthogonal resources. As any multiple access scheme, these techniques need multi-user detection algorithms at the receiver in order to separate the messages transmitted by different users. Most SCMA schemes apply the message passing algorithm, or MPA, due to the intrinsic sparsity of the system model. MPA exploits this sparsity and provides a receiver algorithm with significantly lower computational cost when compared to optimum detection using maximum a posteriori or maximum likelihood techniques. So in this work, we consider SCMA in an uplink scenario with single antenna users transmitting to a multiple receive antenna destination node. In the paper, we extended our threshold-based edge selection multi-user detection algorithm to systems with multiple receive antennas, and we also proposed a receive antenna selection algorithm as an alternative solution to exploit antenna diversity during MPA calculations. Now I will detail the uplink SCMA system model. SCMA is strongly based on resource allocation with sparse signatures. Consider J users transmitting over K shared resources. The resource allocation matrix F has K rows corresponding to available shared resources and J columns with the corresponding users' signatures. Load factor is named beta and is calculated J over K, which is assumed to be always greater than 1. That means overload condition, more columns, users, than rows, resources. We see here the benchmark allocation matrix 4 by 6. Note that in each resource we have users colliding. The collision or row degree is named dF. Also, users spread over a certain number of resources out of the total available number. We name this N, the spreading degree, which is typically much lower than K. Taking one user column, here for instance from user 2, we observe its spreading signature, which can also be represented with a spreading matrix if desired. Since users spread over many resources, SCMA considers information as multidimensional symbols instead of multiplexing information into single dimensions. This is a major difference to power domain NOMA. So SCMA symbols are jointly decoded, considering its multiple dimensions over the resources. Thus, we introduce the concept of SCMA codebooks. We assume that all users map its information bits to a M-ARY modern codebook, where each code word has n complex dimensions. Then, taking the user-specific spreading signature, each user transforms the modern codebook into a user-specific sparse codebook with k complex dimensions. The sparse version of the codebook of user J is named calligraphic xj. Note that k minus n of these dimensions of all its codewords are null values. SCMA is a physical layer scheme. On top of that, we consider that a forward error correction code is employed. Thus, a long-coded message must be broken into several bit packages. Each bit package is mapped to an SCMA codeword to be transmitted in one channel use. The receiver must extract soft bits from all SCMA packages in order to perform iterative detection and decoding and recover the original coded message. This is an illustration of mapping from two-dimensional modern codebook to a four-dimensional sparse codebook. The user signature here is from user 2. The design of the codewords of the modern codebook is not the scope of this presentation, but this is crucial to the final SCMA performance. Here we show a simple codebook based on a repetition code, which is a particular case of SCMA named low-dense signatures. Finally, the received signal model is the superposition of all transmitted sparse codewords from all J users. affected by each fading channel. Since we consider multiple receive antennas, there are NR copies of the signal, with different fading channels. We assume Rayleigh fading channels constant during all the channel uses necessary to receive all the packets of one coded message. Later we'll drop the package index I and focus on the SCMA detection algorithms. Additive white Gaussian noise is also present. This illustration shows the graph representation of the resource allocation matrix. Multi-user detection is generally done exploiting algorithms over this graph. Message passing algorithm is the basic framework for detection. However, when NR receive antennas are considered, each function node is actually extended with different fading gains. The extended version of the function node showed in this illustration, considering 4 receive antennas, reveals that MPA has multiple copies of the same graph to work with. Since users transmitted only one SCMA code word each, the variable nodes are not duplicated. Now I will show the proposed multi-user detection algorithms. I will start with the extension of our previous work on edge selection MPA. Initially, we considered single antenna receivers. The function nodes observe collision of users that have spread in the specific resources. The core idea here is that when trying to estimate the probability mass function of the code words of user J, the function node can simplify the exhaustive interference cancellation tests intrinsic in the MPA. To do that, we identify the strongest user colliding with user J. Here we show an example in function node K1 where 4 other users collided with user J. The strongest one has a fading strength of 5.1. We set a threshold of 50% on this strongest value to discard any user which has fading gain weaker than this threshold. Weak users will be treated as noise by Gaussian approximation, in this case the dashed dot lines. The remaining strong users, with bold lines here, will be considered in the more expensive MPA calculations, some kind of exhaustive search for the most reliable values for interference calculation. In the other function node, many of these users have weak fading gains and many of them are going to be treated as noise, while only the strongest one will be considered in the more expensive calculations. The result is that by tuning the threshold, our computational complexity order ranges from linear, meaning full Gaussian approximation on the interference, to maximum, meaning that no user is treated as noise and MPA is performed in its original complexity order, which is exponential to the collision degree. Thresholds between 0 and 100% of the strongest interference will lead to a random complexity in between these bonds. Details of the complexity order analysis for this algorithm can be found in our previous paper. Extension to multiple receive antennas is straightforward. The main difference is that now the messages must be calculated considering the reliability observed by all the extended function nodes from each receive antenna. We simplified the math showing these equations where A is a power scaling due to the SNR in this function node and this specific receive antenna. C is the extrinsic message showing the reliability of the variable nodes on this interference for user J. And B is the maximum likelihood equation for the function node when trying to estimate the probability of projection A from user J. Note that the equations are in the log domain in order to apply log MPA, reducing the number of multiplications of the algorithm. Max star operation over the extended function nodes indicates that antenna diversity will provide more reliability in the message sent to user J. Now we move to our novel proposed algorithm for this scenario. Herein we call this algorithm antenna selection MPA. Consider calligraphic R being any subset of the set of receive antennas. We propose the heuristic metric of the signal to interference ratio, SIR, in function node K when estimating the probability of a projection from user J as the following equation. On top, we have the power of the sum of fadings of user J over this subset of antennas. In the denominator, we have the sum power of interference from users that collide with J in the same function node, mixing fadings in the same subset of antennas. We defined that the best subset of antennas to be used in the message from K to J is the subset that maximizes this heuristic. This must be done independently in each edge of the graph when calculating function node messages to variable nodes. The complexity of finding the best subset increases exponentially with the number of receive antennas. Once the best subset is known, the signals from different antennas are mixed in a selection combining manner, resulting in a single function node observation. Two major points must be noted. The chosen subsets minimize the function node interference of each user independently in each function node. The graph is reduced to an equivalent single antenna graph. However, edge selection was performed intrinsically in the extended nodes. So in the simulation, we noted that applying full Gaussian approximation on the remaining interference of the equivalent graph leads to similar results as performing original MPA, but with much lower complexity. This is the major benefit of this algorithm. Now I will show some simulation results. The fixed parameters in all simulations are the following. Benchmark SCMA system with 6 users spreading over 4 subcarriers. The model codebook has 4 codewords and 2 complex dimensions based on APSK projections to optimize minimum Euclidean distance, and the collision degree in each function node is 3. Error correction code is a short block length LDPC of rate 1/2 and block length 128 bits. Inner iterations of the MPA are set to 5 and outer loops are set to 3. This figure shows the results of extended threshold-based edge selection algorithm to multiple receive antennas, varying the threshold from original MPA dashed lines to full Gaussian approximation solid lines. We note that increasing the number of receive antennas increases the slope of the bit error rate curves as expected due to the spatial diversity. With respect to the threshold of the extended threshold-based edge selection algorithm, we observed that by adding more antennas, we increase the range to tune the performance and complexity, allowing for better fine-tune in between the two bounds, as observed by the difference between solid lines and dashed lines. Here we show an elbow curve to fine-tune the optimum values of the threshold parameter, considering the frame error rate of the system. The wider range for tuning shows up with the largest number of antennas stimulated, which is NR equals 4, where the threshold 0.6 provides the lowest computational complexity without compromising significantly the performance. Finally, we show the results of antenna selection MPA. Blue curves are for NR equals 3 receive antennas, and red curves are for NR equals 4. Star markers show the antenna selection algorithm in each case on top of the previous threshold-based simulations. Also, note that antenna selection MPA applies full Gaussian approximation. Its main cost is finding the best subset of receive antennas for each function node. We observe that for NR equals 3 antennas, the antenna selection MPA has better frame error rates than the original MPA up to 14 dB of EB and 0. Then performance matches the original MPA. Therefore, here antenna selection MPA has the better trade-off with respect to performance and complexity. Now, in the red curves, for NR equals 4 antennas, we observe that antenna selection MPA has an intermediate performance between original MPA in dashed lines and full Gaussian approximation in solid lines. There seems to be a loss of diversity due to the subsets of antennas chosen based on the signal to interference ratio. Still, its computational cost may be worth it when compared to the original MPA. So to summarize, we have presented an extension of threshold-based edge selection Gaussian approximation MPA for SCMA systems with multiple receive antennas. Simulations have confirmed that receive antenna diversity is preserved, and as the number of antennas increase, we have more room for tuning the trade-off between complexity and performance. Also, a receive antenna selection was proposed to be used along with Gaussian approximation in the MPA's function node calculations. This novel algorithm provides a trade-off between performance and complexity for the benchmark SCMA system when compared to threshold-based edge selection Gaussian approximation, and may also be more scalable for a small number of receive antennas and larger SCMA codebooks. We appreciate your time and the interest in our work. We also thank the agencies that have partially supported this research and some of the authors. This is our contact information in case you want to reach out to us. References will be available in the slides document. Thank you very much.